Okay, thanks everyone for coming. This is the first of our Center for Multimodal Neuroimaging presentations. We're planning on doing these seminars every other month, and then in the months that we don't have these, we have our usual walk-up sessions at either the atrium of Building 10 or just outside the cafeteria in Building 35, where you can come ask members of the different CMN cores questions about how you can do multimodal neuroimaging, or if you're stumbling through something in data analysis, hopefully we can address those. So look at the emails. And also, if you noticed in the last email that I sent out, we now have a mailing list. So if you want additional email messages from me, because who doesn't want more email, go ahead and subscribe, and then you'll get additional things that range from helpful tips to whenever we're posting new content to the website. So today we have, very graciously, Javier, Dan, and Vinay presenting about the advantages of multi-echo FMRI. It is a very introductory, very interactive presentation, so feel free to raise your hands and ask questions throughout. And with that, I will turn it over to Javier first.
Thank you. So as Pete said, this is going to be very basic, just so you have a feeling of what multi-echo data is and what it can do for you, hopefully. I'll be covering the first two parts, which, as I said, is just what it is, how it compares to single echo fMRI, and then a few of the basic things that you can do with this data that it's richer than your regular data. Some of them you should do them, some of them you shouldn't, but I talk about them so you start to get a feeling of what's on the data. And then Dan will talk about perhaps what's the most interesting part, which is the one of the many things that you can do that's trying to automatically denoise your data, and Vinay will talk about what is available here to acquire this type of data. So before I move any further, here are a couple of links to places where I think you can get a lot of additional information that might be very nice. The first one is part of the TEDANA project, which is something that Dan will introduce later. It's an attempt at rewriting a new implementation of the MEICA somehow algorithm, although somehow modified. And they have a lot of links to some of the original papers, to some of the talks about multi-echo that's been on OHBM and some other conferences, and I think it's a really good place to start. And then every summer here, Peter organizes the summer course, and I think at least for the last 3 years, there's been a talk on multi-echo. In fact, most of what we're going to talk here, it's on those talks, and the videos are publicly available, and that can be another good place to go for information. So, first thing, just so nobody gets confused, this is not multimodality. I guess we're here because of the word multi in multi-echo, but this is just fMRI, okay? So that's the first thing. Now, how it differs from your regular single echo fMRI. So fMRI, it's about acquiring data across time, because then we're going to look for fluctuations of interest, either intrinsic ones or fluctuations that follow our experimental paradigm. And what usually happens is we acquire one volume per TR. Those volumes are acquired as a series of slices, and basically we have a single excitation. For each excitation pulse, we read out the data just once. We open the readout window at a time called the echo time, which is the distance between the excitation pulse and the center of the readout window. We do that for each of the slices, we do it across time, and the final result is we have a single time series per voxel that we acquire at a given echo time that hopefully we chose in a smart way so that it maximizes ball contrast on average across the whole brain. Usually you would choose an echo time that is equal to the average T2 star of your data. And unfortunately, because not the whole brain and not even the whole gray matter has all the same T2 star, you have a balance of getting better signal in some areas than in others. So what is multi-echo? Multi-echo, what we're going to do is instead of just reading out once, we're going to be reading out several times. In this particular case, 3 times. So what this means at the end of the day is that we're getting more than one time series per voxel. We have pseudo concurrent estimates or measures at different echo times, and not only we have more data, but we have several traces per voxel that differ in what hopefully will convince you in interesting ways that would allow us to separate what are fluctuations of interest from what is noise, and hopefully in a pseudo-automated manner. And we're going to do this at no additional SAR cost, because there is no more excitation, we're just reading out more. There might be a slight loss in temporal resolution because we want to read more times. We might not be able to pack things as much as we were doing before, but I wouldn't consider that a big problem because you can combine multi-echo with multiband, which is a completely different thing that allows you to scan faster by concurrently acquiring several slices and then pulling them apart. But there are sequences that can do both things for you. Vinay will tell you which ones are available in which scanners. So I wouldn't worry too much about the temporal resolution. And then you could argue that maybe there is a slight loss in spatial resolution because sometimes, depending which one is your later echoes, you may not want to have two small voxels, so you have some signal left, but there's a lot of balance there. So I would say the take-home message is that you can get all this extra stuff with almost no loss or no loss at all. And as we will explain, you can either use it, or if you acquire your data in such a way that one of these echoes would be similar to what's your regular single echo, you could do a first analysis in which you just look at your echo 2, and maybe if your effect size is strong enough, that's good enough. And if not, you can do several things that go from simpler to more complicated in order to hopefully improve the final signal-to-noise ratio of your data. Is that clear? Right. So how does it look? So here's just an example of a given volume of some fMRI data at the different echoes. And we can start to see one of the first advantages that this gives us is that in these areas that there is a lot of signal dropout in your regular echo. So in all of the slides, the idea is that echo time 2 here was acquired would be your regular single echo. So we can see that by having also acquired data at earlier echoes, we have recovered signal in some regions. The later echo doesn't seem to do better in that sense, but it will also give us some information. But the first take-home message is that if we find a smart way to potentially combine all this data, we might be able to be recovering signal and TSN in areas where we have problems before. So in order to understand what can we do with this data, I'm sorry I'm going to have to throw one formula, but it's the only one, just so we can have a little bit of a discussion of how the data looks and what's in there. So here we have time series for 6 voxels, and basically the signal at a given voxel, at a given time point, and for a given echo looks like this, mathematically speaking. And this has two important or two clear components. We have one component, the S0, that captures local fluctuations due to T1 changes, hardware instabilities, things that we usually don't want, and that account for quite some part of the variance in the data. And then we have a second component that captures changes in R2 star, which a big proportion of that is going to be the fluctuations that we really care, the ball effect. We can look at each of these two components as having a mean value and a small fluctuation sitting on top that is really small compared to that average value. And that's true both for the S0 component and for the R2 component. And we're going to see as a first step that because we have this richer data set, by acquiring data at several echoes, we're going to be able to hopefully separate all these different chunks that are present in the data. And hopefully we will be able to get to having almost just this guy, which is the one we care about. That doesn't mean that this guy is clean. There might still be some physiological noise in here, but definitely will be cleaner than when we have the whole thing. That's one way to think about it. So one thing that we can do, and I'm not going to go through the math, and this is not that interesting, but the initial thing you can do, you can estimate average map of S0 and average maps of R2 star. And we can see that they start to capture different aspects of the data. So for example, the S0 map seems to capture the intensity and homogeneity that comes from having a specific configuration of coils and part of the brain being much closer to the readout coils. And here we have a very perhaps precarious, but still useful, as we will see, map of estimates of R2 across every single voxel. And this we will use later. And we can start to see things like in these areas where we had issues, it seems the estimate's much lower. And we can also see that the distribution of R2 star is not homogeneous across the brain. We can also attempt, although this I don't really recommend because the system of equation that leads to this simple separation it's not perfect and noise can get easily amplified. But in principle, we could also try to estimate both the small fluctuations that are due to S0 or the ones that are due to R2 star. So here what we have is 25 voxels. And here what we're looking at initially is the time series for one of the echoes, the middle echo. This is resting state data. So hopefully some of the little fluctuations sitting in here are very informative. but also we can see that all these voxels have quite a big drift across time. Well, by doing a simple separation, we can get the delta R2 star fluctuations, and we can start to see that in many of the voxels, things seems to work okay, because this one came free of the drift, but we can see that in some other voxels not that well. And this is because, you know, this very simple procedure is really not the way to go. But we can start getting that feeling of how things separate. And if we were to do the same thing in these voxels, we can see that it seems that, you know, the drift and part of the fluctuations went into the delta S0. If we were to take this data and do Instacore with a seed in this location, in the original data, we can see that because it was very contaminated, because I didn't do any detrending or anything. I mean, this is just on the raw data. We see this pattern that doesn't look very brain-like, because it looks like you have this correlation of this seed with everything on this side. If we were to do the same thing on the delta S0 time series, we can see that it seems to capture that. And if we do it on the delta R2 star, it seems that we start getting a cleaner map. Again, this is not the way to go, but I hope it starts showing the potential power that this data has. So another way to go around it is to think, okay, we have 3 concurrent measures per voxel. Let's try to combine them in some way. Because, you know, even if simply the thermal noise is it's non-correlated across them, just by adding them up, a simple weighted average might help us. And the first thing you can do is a simple summation, but that might not be the best thing to do, because as we saw, the later echo, even though it had information, it might actually add more noise than information in some cases. So people, and I recommend this paper, had looked at better ways of doing it, and one of them is this one that we tend to call optimally combined, in which it's a weighted average that first you get that T2 star map estimate, and then you use it to combine the data using this formula. And what we will see is here we have the single echo data. Here we have the optimally combined. We can see that by doing that, this is just one volume, we have started to recover some signal in these areas that were problematic. I mean, it's not perfect, but definitely it seems that the hole here is much smaller. And if we were to think of this in terms of TSNR, we can see how we have gained TSNR all over the place. I mean, not just in these bad areas, because you can compare here to here. This is the same scale. But also we have recovered enough signal that suddenly maybe we can start doing analysis in these regions that before we didn't even have a chance. And the last part that I'm going to talk about before Dan takes over is this idea of echo-dependent analysis, because this is kind of the basis for MEICA and some of the other more advanced ways of denoising the data that might be what you want to do. So again, here is the original formula that we have, and let's assume that here what we have is the decay, the change of signal for different echo times, and we have already assumed a given S0 for this voxel and time point, and a given T2 star, and the inverse is the R2 star. And we're going to assume that from one time point to the next, there is a little bit of activation. There is some ball effect, a change in T2 star. What that means is that we will have this second decay. You know, the only difference between this one and this one is being a slight change in R2 star, which is what really activation, neuronal induced activation, hopefully looks like. Instead of looking at these two curves separately, we can just look at their difference, and this actually gives you the typical curves that are used to choose the optimal T2 echo time that you would use. But if we look at this in terms of signal percent change, we see this characteristic, which is key for what Dan is going to talk about. And it's this idea that for fluctuations that are related to R2 star, they have a linear dependence with echo time. And we're going to take advantage of that principle. Now, we have that on this side. What about the other type of fluctuation? What about if between one curve to the other, the change is not in R2 star, but in S0, okay? Some artifact. Then that's how the two curves would look like. The difference of the two curves start to look very different to what we had before. But what's interesting is that in terms of signal percent change, fluctuations that are non-ball don't have that linear dependence with echo time. And it's this difference that we're gonna exploit in the rest of the things that Dan is gonna talk about. So any questions for me? I mean, I can take questions at the end too, but if not, I'll give the podium to Dan. Yours.
Okay. So a chunk of what I'm talking about is this method called MEICA, which was developed here, led by Prante Kundu back when he was in SFIM here. And just to sort of go take a little bit of a big picture of where Javier left us, the methods he's described so far are useful. Most of them have been around since 1999 or so. But the limit is every calculation is sort of done separately per voxel per time point. So every single voxel has a time series, and every single time series you're making some sort of model fit or some weighted average. And that can help, but you're leaving a lot sort of on the floor. So the big innovation that Pronte came up with was leverage echo relationships across voxels in time for noise removal. And I was trying to think of sort of the big take-home principles of this. And the first is, the idea is to sort of figure out what's bad. You don't care what's good or what's better. You want to know what you want to get rid of. So the idea is to figure out what you want to get rid of. And ideally, the process should be completely automatic and based on MRI physics. So there's a bunch of denoising procedures over time that are based on sort of our common sense of what MRI signals should or shouldn't look like. So the classic one is detrending, where we know there's a linear drift, and we know that linear drift is almost always scanner noise and not T2 star weighted, and not R2 star weighted. So when we analyze our data, we just remove it. And that works really well. But if you have a study, but it's based on sort of an assumption of what we know about the data, and that's an assumption that's almost always true. But there's a lot of assumptions we make that are a little bit more gray area, like, yeah, this blob is mostly in gray matter with a bit of white matter. This blob is a little bit on the edge. How much off by the edge do you say is a motion artifact versus brain? So a lot of the denoising methods sort of make assumptions about what we think is good or bad. And if these assumptions can be rooted in the physics, we can be more confident that whatever things we're doing are going to be right. So I'm starting out with where Javier left off. We have three time series, and those time series, at every location can be divided into this, for the R2 star signal, the that should be containing the bold weighting. It could be the changes are linear relating to echo time, and for the S0 signal, which is the stuff that we want to get rid of, it's most likely to be constant across echo time. So the MEICA approach is you take your time series and you do ICA. So you essentially change your data is originally space and time. You split it into components in time and space versus components. And these are the inputs to MEICA denoising. And the way it works is you can now look at each of these components. So this is an example of one component that is probably bold weighted. So if we just look at this component, what you're seeing is the hot spots, the red blobs, are in grayish matter. They kind of are symmetric. If I showed this to anyone here, they would say, yeah, that's probably bold related. But if you look at this per echo, what you're seeing is the weighting of this component per echo is increasing by echo. And if you do this linear fit, you get this other map of sort of that sort of says that collapses the idea that these numbers are scaling by echo. It collapses this into a single image. So the terminology used here, and I think this is the main formula that I'm using from here on out, is essentially a very simple summary statistic, which is we call kappa values are going to be how R2 star weighted the signal is. And that's essentially you're multiplying this ICA map, so where is the most signal in this ICA component, by this fit map saying how linear does the change scale with echo time. So you're multiplying that across all voxels, and you're taking the sum, and that's kappa. And you could do the same thing for S0 on the same component. So if you fit this signal to the S0 model and you say how much of the signal is constant across echo time, for this component we see a fairly flat map. And we see that not much fits over here either. And in this specific case, kappa is really high and rho is fairly low. So likely this component is being more contributed with the R2 star signal we want to keep than the the S0 or rho signal that we want to get rid of. Here's another component from that same ICA data set. And here what we're seeing is there's a ring around the side, which, if we look at that, we might say is motion. But that ring is equal magnitude across echoes. There's some R2 star weighting in this, but there's a much stronger S0 weighting in the signal. And in this case, we see that rho is 81 versus kappa 32, which means it's very likely that this is going to be a primarily noise component. So then the trick comes to say, we can sort of look at this ad hoc, but where do we set the cutoff of what we want to get rid of? So the way this was originally approached was you can have all your ICA components, and these are the kappa values for every ICA component. So how R2 star weighted is. If you sort them by this kappa value, what you can see is there's a bunch of components with higher kappa values, and at some point they kind of drop off. And with some frequency, it's not always this clean, but we see some sort of elbow point. And what we could say is, let's look at the stuff, let's look at the top, in this case, 8 components that are on the left side of this elbow. And these are what the ICA components in their time series look like. And you can see they all have high kappas, low rho values. So these are components that are likely to stay in our data. But what you can see, so this is just across a bunch of subjects, and you can see the same sort of pattern repeats. Sometimes the elbow is cleaner, sometimes less clean, but there's always sort of this general shape. Not usually this general shape, as I saw some people raise their eyebrows. On the other hand, if we look at the components in the bad end of this curve, so where kappa is low and rho is higher, this is what they look like. And these are the artifacts. Just by looking at a lot of these look like motion and other stuff. High frequency signals, that's probably respiration or cardiac. So these are the components. By just looking at this curve and setting some threshold, you could say, let's get rid of these. And you get rid of these, you reconsider your time series, and that's called the denoise time series. To sort of just quickly go, I'm not going to go into the full guts of the MEICA algorithm here, but to just sort of go over the general major steps. You still have to pre-process your data like usual, so whatever you like to do, slice timing, head motion correction, if you want to register it or anatomical or not, that's not critical, but obviously it's frequently done. Then we optimally combine the echoes. So this is what Javier was talking about earlier, which is you take a weighted average of the 3 echoes, and the weights are based on what we think the bold weighting should be. So that goes back to the work by Posse back in 1999. Then you take that, you do a principal component analysis. And then so PCA is very frequently a predecessor for ICA. And these are just 2 ways to reduce the data and turn it into components. And then the output is the denoise at the very bottom, which is task arrest. So just to break these down just a little bit more, for the PCA, there is actually a component characterization already in there, which is used essentially just to reduce the dimensions of the data, which in theory makes the ICA work better. And when it works well, that's going to remove signal that is clearly is more likely to be noise. And then again, when you have the ICA, you do the ICA decomposition. You characterize each component by kappa and rho. You do component selection, which has a bunch of different decision factors, including that elbow test I was just showing. And you generate the denoise time series that goes into the analysis. So now I'm going to review some publications, some work that has used this to highlight some of the benefits. This is not an all-encompassing review of everything everyone's done with MEICA. It's not even an all-encompassing review of all the things that have shown useful stuff. It's just to give you a sense of ways people have used MEICA that get us something that would be hard to do without MEICA. The first one of these comes from Jen Evans, which is one of the things that is really hard to do is look at slow signal changes. So she designed a study to look at several ways of subtle changes that are often lost if you do classic detrending. Because this, in theory, would be able to separate a slow drift that is bold-weighted from a slow drift that is not bold-weighted. So the first experiment she did was she had a very long block design. I'm blanking on the duration. I think it's about a minute. So this a minute block design is usually 3 minutes? What's it? Oh yeah, okay. 3 minutes. So it's a very long block design. So this is usually going to be completely washed out if you do any type of detrending. And just to give some variation, she had a very slight amplitude change, I think, in the contrast of the images. So if you do just the optimally combination of the 3 echoes, this is what you get. And you can see that there is a response, but it's essentially at baseline because you have to, there's no centering. If you detrend it, you get this, but sort of you're kind of mixed on where the baseline is. But if you do denoising, it shifts this up just a little bit and makes it just a little bit cleaner. That amplitude change doesn't come out quite as strong, at least in this visualization. The second version of this is if you do that same 3 minute thing, but you're shifting, you're making one a little bit longer. And again, with just the 3 echoes, it's really hard to see this difference. If you detrend, everything is kind of shuffled and baseline. If you do the whole MEICA denoising, then you're actually seeing this a little bit more robustly. The final one, which I think is the most critical, is a true slow drift in your signal. So you're seeing over the whole time course, you're seeing your contrast slowly decrease using 2 different shapes. And this is critical because if people are talking about, let's say, pharmacological studies, where you're trying to do a trace, like some sort of chemical tracer, and you want to sort of see how the bold response changes over time, that's going to get killed by detrending, as you can see here. So without detrending, it's flat. If you detrend it, you literally have nothing visible. But if you do this, it separates in visual cortex the bold-weighted signal drift from that detrended, and you actually get the signal you're wanting. So this opens up the potential to do things like pharmacological studies with FMRI that have slower response changes. The next example is a particularly difficult area to image is brainstem areas, because you're right near a lot of arteries and veins. I guess arteries right there. You're right near a lot of arteries. There's a lot of pulsation, breathing, dropout. You have essentially the works of MR physics that cause problems in imaging is right around the brainstem. And if you want to hit an area like the superior colliculus, it's really hard. So there's a bunch of approaches that have been tried with this over time. One is what's called cardiac gating, which is you don't collect at an even time rate. You collect at essentially, you lock each volume to when the heart beats. But what that does is it changes the spacing between each of your volume acquisitions, which completely messes up your baseline signal. So if you do without gating and you just look at a single echo data, you look over here at the superior colliculus and it doesn't cross a significant activity for this task, which was a music listening task. If you do the raw T2 star estimation that Javier mentioned earlier, again, the superior colliculus doesn't really have reliable activation. If you do the optimal combination, you see a little bit there because we're getting a little bit of a signal boost, but not much. And if you do the full multi-echo denoising, you're getting that superior colliculus a little bit more reliably across the population. Interestingly, one of the original ideas of the study was, multi-echo could benefit us with cardiac gating because it could correct that variation in echoes, and that works. And we do see the superior colliculus here better than the others. But the interesting part of this is it turns out that, with or without gating, multi-echo is better, gets us this hard region more reliably. So if you're really trying to image in these challenging regions with like extravascular artifacts or other sources of noise, multi-echo might give you that just added little edge to more reliably get the signal you want. The last study I'm showing is one of the main questions I often get is just, what is the magnitude of this typical signal boost? So in this study, we scanned 2 subjects across 9 sessions. So it was over 100 5-minute runs of a block design checkerboard task. So the, sort of a classic hit the visual system as hard as possible. And what's nice about this data set is we can look at each run separately, and we can sort of get a massive calculation of how reliable our measures are. So for every single one of these 100 runs, where's my pointer? I had a ROI on the Calcrin sulcus, which is the blue dot. So every dot is from a different one of the Calcrin sulcus, or the lateral nucleus, which is one of these smaller, more subtle regions. Those are the red dots. What I'm showing here is the contrast to noise ratio for that block design task. And if we look, and so the first thing to notice, of course, is the LGN has lower contrast to noise than visual cortex, which makes sense because it doesn't respond as robustly to visual cortex to something as like a flashing checkerboard. But if you look at the echo 2, that's sort of the equivalent of single echo data, versus optimally combined, which is that weighted average. This diagonal is not a fit. This diagonal line is unity. So that means they both have the same contrast to noise. What you're seeing here for this subject, for all 100 runs, in every single run, doing the optimal combination gives you more contrast to noise than you would have had otherwise. And that boost varies from about 2% to 10%, both in the LGN and the Calcrin sulcus. In other parts of the state, I've shown that essentially you're getting the LGN more reliably significant in individual 5-minute runs. Then we add on the denoising step and compare that middle echo to denoising, and what you see in almost every run, that contrast to noise boost is even higher. So this is from like 8% to 20%, depending on the run. So again, this shows you that the denoising really does boost your contrast to noise. The one addendum to the story, which is a little bit more mixed, is if instead of comparing to the baseline of echo 2, you say, how much does this denoising improve us over just the weighted average? What you see is in almost every run, denoising helps. But there are some runs where it's, the help is very small, and some runs where it drops your contrast to noise just slightly, particularly in the LGN. So what this says is, yeah, this is a big deal. Yes, this is a boost above optimally combined, but there are still some factors in this analysis that mean that some days are going to be better than others in how this actually works in practice. So this goes into the last section of my part, which, yeah?
I mean, I think that another point here is this,
Yeah.
the key aspect of both the echoes is that it helps remove these artifacts, but
Yes.
it doesn't necessarily boost the contrast.
Yes.
More than optimally combined.
Yeah.
So,
It shouldn't make it worse.
right.
I think that's, like, if this was sort of on the line or above, I would be very happy. The fact that in about 10% of the runs, it's making it worse is what is less ideal. So this gets to the last section on limits and ongoing efforts. So far, when I'm talking about this algorithm, I've sort of done this hand waving of saying we got the cap and the row, we got the elbow, and we make a cutoff in some principled way, and that's how we decide. The truth is a little bit more complex. I'm not going to go through every single step here, but there's a bunch of different, there's actually a fairly complex decision tree. And I'll say this slide is taken from Javier's summer course, so if you want to hear it sort of gone through in more detail, you can look at the summer course from last summer, and I'm sure he did a phenomenal job on this slide. But so you have, various thresholds on, you make some threshold for kappa values to keep, you make some thresholds for row values to reject, and you set them, you set thresholds on how much bigger kappa should be than rho, you set thresholds on how well it should fit different models, and these are all combined together in a fairly complex fashion. And over time, what's come out is the decisions made are good, but they work better on some data sets than others. And there are still some open questions on this. So which of these decisions are robust against any data you can throw at it is an open question. Which of these thresholds that were set are sensitive to the source of the data? And most importantly, are there changes to be made that can make sure that this is, at minimum, it never gets worse than what we're getting from optically combined. It's always giving us some amount of improvement. So as part of this effort, there's an international group of people, actually, who have been working on sort of refactoring the code from square one with the idea of making a code base that is both more understandable and more editable. So if researchers somewhere want to say, like, I want to see, really dig into this method, understand and change things and tweak things and innovate beyond what we have now, this is a place where they'll be able to do it. And over the past, it's primarily took off last summer, I'd say. That's when it really started ramping up. And over the past year, there's been an immense amount of work on this. And it's to the point now where you can download it and run it. And it will give you results. I think there's still issues before I'd recommend people switching from this. I think it hasn't been validated enough yet to recommend switching to this versus if anyone's using the original version written by Prante Kundu. I would not recommend that yet. But I believably think that it's going to cross that point in the next 6 months or so. So this is something to keep an eye on. The other nice thing here is the read the docs, so the instruction manuals for this is where they're trying to build one of the better explanations of what's actually done sort of in the algorithm and understanding what's happening. So if you want to sort of go to the math, see the reference papers in one place, they have a list of every paper that's published using multi-echo. This is a really good starting point, at least to understand the method more. And with that, I will switch to our last speaker, FMRI. Oh, actually, any questions before we do the transition, or? Okay.
All right, so one thing that has frustrated us a bit is like no vendor has a product implementation that lets you do this. So the fact that we can do this here at pretty much every single scanner we can scan on is we're lucky in that respect. So with our GE scanners, we started off with the basic EPI sequence. Because of some internal design limits and how many dimensions were available to us, we weren't able to do as clean an implementation as we were able to on the Siemens. But we have, we have a sequence that runs on the scanner, reconstructs on the scanner. Because of these quirks, you have essentially one series of images where your echoes are mixed up, and you have to use a script that we provide to separate them out and build your data sets. But we've had that going for several years now. It's a fairly well understood problem and solution. This sequence is also the only one of all our multi-echoes that have gating capability. So this is the sequence that Javier used in that work on the calculus, and Andy implemented that for us for that paper. On our 7T, your best bet is the CMRR C to P sequence. So originally the CMRR sequence was only multi-band capable, but eventually they iterated and added multi-echo. And this work on the sequence is ongoing, and it's updated every few months, so that's your best bet if you're doing it on Error 7T. I believe that the NMRF is taking steps to make this available on the NMRF 7T as well, but I'm not sure where they're at with that yet. And on 3TD and the NIAAA 3T, we took the Siemens product EPI sequence and with some very simple tweaks added in multi-echo capability. So those sequences are able to acquire up to 8 echoes. They separate nicely and cleanly in your DICOM series, so those are just ready to go, and you build your data sets from the individual subseries. Multiband, the CMRR sequence with multiband and multi-echo is also available on these platforms, so that's another option if you want to leverage that and you have different needs for your experiment. To my understanding, so our implementation on 3TD and the NIAAA 3T, it's not gating capable. I'm not sure whether the the CMR has that capability or not, but we're not able to add that capability because we don't have source code for that version of the sequence. All right, and any questions?